Hi students, today we'll do a short recap on chapter 6 electrolysis. Now I've picked this chapter to do a recap because many students feedback to me that they find that this chapter is rather confusing, especially on the part where you have electrolysis of solutions of different conditions. So today we're going to have a quick recap for you to have a quick grasp and understanding on that particular subtopic. Right. Okay, so over here, you can see that I've actually combined the electrolysis concept, all right, electrolysis of molten compound and electrolysis of solution in one A4 size paper. So in one shot, we're going to do a recap for electrolysis of molten compound and electrolysis of solution. Now, the first thing that students understand is that if I have a molten compound, say for example, if I'm given a molten copper 2 chloride, inside this molten compound, I only have the chemical ions, copper 2 ions, and also the chloride ions. But however, if I'm given a solution, all right, inside the solution, besides having a chemical ions, I do have water ions as well. All right, for example, if I have copper 2 chloride solution, inside this particular solution, besides having copper 2 ion, chloride ion, we also have hydrogen ion and hydroxide ions from water. So that is the main difference between molten compound as well as a solution. So molten compound, recap again, only consists of the chemical ions. In this case, only copper 2 ion and chloride ion. But if you have a solution, means your chemical has been dissolved in water. So therefore, in a solution, you will have the chemical ions, in this case, copper 2 ion, chloride ion, as well as the ions derived from the water. For example, hydrogen ion and hydroxide ion. Okay, so we're gonna look into the electrolysis of this given substance one by one. Right, first thing we will start off with electrolysis of molten compound. And in this case, I specifically use example copper 2 chloride. So when you look at the setup to run the electrolysis of molten compound, I will first get a crucible and I will put in my solid copper 2 chloride inside. Then I would immerse my carbon electrons, which has been joined to a battery using a connecting wire. So to start off the process, I will start heating up my substance in a crucible and until my copper 2 chloride melts. So once it melts, you get your molten copper 2 chloride. So your substance begin to able to conduct electricity and the electrolysis process will start. All right, so to analyze this particular process, we will first need to identify what is the cation and the anion found in molten copper 2 chloride. So in molten copper 2 chloride, all right, the minute electrolysis started, the ions will get separated. The cations that you can find over here is copper 2 ion, and your anion is the chloride ion, Cl minus. All right, that's the only cation and anion that you have. All right, so now we will continue. So once the ions are being separated, they will move to the respective electrodes and get discharged there. So cation, the positive ions, will get attracted and move towards cathode, whereas anion, the negative ion, will move towards anode. Now, once they reach their respective electrodes, they begin to discharge. Now, many students do not understand what is the meaning of discharge. If you look at the word itself, discharge means you are removing the charge. You are removing the charge. And you either remove your charge by accepting electrons or donating electrons. So we do a quick recap at this time. So for ions to discharge or to remove the charge, like what I mentioned, they either accept or donate electrons, right? Now, if you're talking about positive ions, those that carries a positive charge, they will normally discharge by accepting the electrons. They will discharge by accepting electrons. But however, if you have negative ions, so if you have negative ions, one that carries the negative charge, it will discharge by donating the extra electrons. Now, some students need further clarification on this matter, so let me just continue a little bit more. So, say for example, if you have let me just move this one to another page. Huh? So that's easier for you to see. All right, so we are talking about discharge process. So you have discharge process. All right, positive ion discharged by accepting electrons. For example, if you have positive ion Na plus, all right, Na plus, from the formula itself, you understand that Na plus has lacked one electron. So in order for it to remove the positive charge, it needs to accept one electron. Accept one electron. Right. So one more example, how about, let's say if I have Mg2 plus magnesium ion. So this is a positive ion. If you want this positive ion to discharge, it needs to accept 2 electrons. So on and so forth. All right. Now, how about negative ions then? For example, if I have a chloride ion, Cl minus, right, it will discharge by donating 1 electron. All right. Let's say if I have oxide ion O2 minus, so let's continue from here. If I have O2 minus oxide ion, it will discharge by donating 2 electrons. Right, so this is the key concept of discharge process. So always remember, positive ion discharge by accepting electrons, and negative ion discharge by donating electrons. All right, and how many electrons that it accepts or donate, it depends on its charge. Okay, so with this key idea, we go back up again. All right, so again, we are at electrolysis of molten compound, right? So ions, so we have CO2 plus moves to cathode, Cl minus moves to anode. So ions that get discharged at cathode, of course, CO2 plus get discharged at cathode, and Cl minus will get discharged at anode. And now we try to write a half equation to show people the discharge process. So normally half equation is an equation that you tell people what's happening. All right. So what happened is the CO2 plus, once it reached cathode, in order to discharge, it will accept 2 electrons. So the accept, I will use the symbol of plus to show it's accepting. So it accepts 2 electrons, and when that happens, it becomes a neutral element with the formula of Cu. All right, so you have CO2 plus, takes in 2 electrons, and it forms Cu. Now, how about at the anode side? At anode side, you have your Cl minus, all right, that reach. So once your chloride ion reach anode, it will begin to discharge. And just now I've mentioned, negative ion will discharge by donating electrons. So how do I build a half equation to show donation of electron? You will normally put an arrow, and then the electrons that's donated at the back, you will write it at the back. All right, so that means to say electrons has been thrown out. Electron has been thrown out. Now to complete this half equation, once you have chloride and it discharged, it will turn back to chlorine, right? But you have learned under group 17, for all group 17 element, it exists as diatomic molecule. So therefore, a neutral chlorine has a formula of Cl2. It has a formula of Cl2. Now, so we have built a half equation to tell people what's happening. But do not forget, for all types of equation, be it a normal chemical equation or ionic equation or half equation, you always have to balance it. Right, so now we look into how do we balance it. So the first thing is, of course, we will need to balance my chlorine. So I will put a 2 in front. And please be reminded just now, when I first started with only 1 chloride, I remove or I donate 1 electrons. So now in order to balance the equation, you need to put the 2 over here just to balance up your chloride, right? Now you have to adjust your electron as well. Because 1 chloride will donate 1 electron. Now since you involve 2 chloride, therefore you will donate 2 electrons, etc., etc. Okay, so with that, I'm done with the half equations at anode and also cathode. Now moving on, the next thing is, most of the time, once you are done with half equation, the question will ask you to build an overall ionic equation. So normally overall ionic equation is the equation that combines the half equation at cathode and anode. So to do that, normally I will rewrite my both half equation. Let me just copy and see. So I will rewrite my half equation. And in order to build the overall equation, I need to combine these two equations. Now, many times students will ask me, so teacher, how do you combine the two equations? The key to combine is you need to cancel off the electrons on both sides. So if you focus on the electrons, here you have 2 electrons in front, and here you have 2 electrons at the back. So to build an ionic equation, all you need to do is you just cancel off the electrons, and then you combine your reactants on the left-hand side and products at the right-hand side. All right, so therefore, imagine now I've cancelled my electron. The reactants for these reactions are Cu2 plus and 2Cl minus. These are the reactants that are found before the arrow, right? So I just continue. And then now I will put my products together. The product from the first half equation is Cu, and the product from my second half equation is Cl2. All right, so then this is my ionic equation. Okay, so this is my full ionic equation. That's my final answer. Hold on, let me do it nicely for you. Okay, so this is my ionic equation. Okay, so we are almost done with the first one. I've shown you how to look at the cathode and anode, how to see who goes to anode. We look into the cation and anion, and then we see who goes to cathode, who goes to anode, how they discharge by using a half equation to explain, and then how do you build an overall ionic equation. Right, now the last bit for us to discuss would be what could be the possible observations for this particular electrolysis setup. Right, normally when you run electrolysis, right, you will have a minimum of 2 observations, one at cathode, one at anode, and sometimes your solution might give you some observation as well. So let's look at what do I see at cathode. Now, for you to do your observation, right, you always have to ask yourself, what happened at anode? What has happened at anode and cathode? All right, so since we are doing cathode first, now what happened as cathode is that the Cu2 plus, I've changed it down to copper. So copper that you form is a solid. And for you to recap, it's a brown color solid. So therefore, at cathode, brown precipitate is observed. Brown precipitate is formed. All right, so this brown precipitate is actually the copper that's being formed. All right, but in observation, we do not write copper form because observation means what do you see? You do not see Cu, but you just see the brown precipitate. So this one is just for explanation. Why do you see a brown precipitate? All right, next, how about at anode? What do I see? Now at anode, what you realize is that you have discharged your chloride and it forms a chlorine gas. So chlorine gas, we do a quick recap. Chlorine appears as gas and is greenish yellow in color. So what we see is that you have greenish yellow gas produced. All right, and let's say if a question asks you, why does a greenish yellow gas? Because chlorine gas is formed from the discharge process. Okay, so that is a quick one on electrolysis of molten substance. All right, so now we shall move on to electrolysis of solution. Now, just now I've mentioned that solution means you have the chemicals that dissolve in water. So therefore, there are more ions found in the solution. Now, in this case, let's discuss what are the cations and anion found. So you have cation Cu2 plus, anion Cl minus. On top of that, when you see the word solution means you have H plus and OH minus from the water. So H plus is a positive ion, it is a cation. So, and OH minus, negative ion, it is an anion. So OH minus here. Okay, so this is H plus and this is OH minus. So as usual, when you have cation, cation will always move towards cathode for discharge purpose. And when you have anion will always move towards anode for discharge purpose. Okay, now let's discuss further. So imagine that Cu2 plus and H plus both reach cathode, Cl minus and OH minus both reach anode. So at the end of the day, which ion will be chosen to discharge at cathode and which ion will be chosen to discharge at anode? This is one part that we need to figure out, because if you can't figure out the correct ions to discharge, your half equations, your overall equations, even your observations, all will be wrong. All right, now how do I see which ion that I should choose to discharge at cathode and anode? So we do a quick recap over here, right? So I will write down, this is a quick recap. So whenever you want to select ions to discharge, always remember the following. Number one, at cathode. So when you want to select ion to discharge at cathode, you will always follow ECS. And I hope you guys already memorized ECS, electrochemical series. And according to electrochemical series, you will always have to opt for the ions with lower position, right? So remember, at cathode, your choice is always based on ECS, all right? And you will always, based on ECS, you will always choose the ions that has the lowest position, because those ions are easily discharged, all right? Now, however, at anode, the story will be different. At anode, your choice can be affected by three factors: type of electrodes, second factor, concentration, and the last factor, position in ECS. All right. So unlike cathode, at cathode, your choice is always based on their position in ECS, and you go for the ions with lower position. But for anode, your choice of ions, right, which one that you will choose to discharge, can be affected by three factors: type of electrodes, concentration, and their position in ECS. So you must pick the correct factor, and based on the factor, you make the correct choice of which ion to discharge. All right, so we recap again about these three factors before we move on to our specific examples above. Right, so type of electrodes. This is the factor that you will choose if better electrodes are used. So most of the time when we carry out electrolysis, we will use inert electrodes. Inert electrodes means those made of carbon, graphite. Those inert electrodes are not going to interfere with your electrolysis process. But however, certain times we might use electrodes that's made up of metal, for example, copper electrodes, silver electrodes. If you use a metal electrodes, your choice at anode will be based on this factor, all right? And the rule for this factor, so let's say if you have picked this factor, the rule that you have to follow is none of the ions will be chosen. So remember, if your factor is type of electrodes, none of the ions will be chosen. All right. So then you say, then how to continue? So instead, the anode itself donates electrons and form ions. So this is the rule. If you have picked type of electrode as your factor, the rule that you need to follow is, remember, you do not choose any ions. The anode itself will donate electrons. So the anode itself wants to take part in the electrolysis process. Right? So now, how about the second factor, concentration? Now, when you will use this factor if the solution given is concentrated. Or some book or some question, they won't use the word concentrated, they give you a figure instead. So if you have a concentration that is above 0.5 mole per dm cube, that solution is considered concentrated. So a reminder, not every time the question will tell you that, oh, you have a concentrated solution. So we might give you a figure that represents that it is a concentrated solution and it's normally above 0.5. Okay, so if you are given this, if you have chosen this factor that affects your choice at N naught, the rule that you need to follow is that based on this factor, you are supposed to choose the chemical ions. Chemical ions, not the ions from water. Right? So normally you would choose the chemical ions, not the one from water. Right? We will discuss more about this if you have confusion. We will look into application later. Okay. Now the last factor that affects my choice is the position of ECS. Right? So again, if your factor is position of ECS, the rule that you're going to follow is you will choose the ions with lower position in ECS. All right. Okay, so with this recap, now we go back up on the application. So through the application, you will understand this thing better. All right, so we go up again. We go back to our situation. Electrolysis of dilute copper to chloride solution using carbon electrodes. The minute I turn on the electricity, the cation ions will get separated, the anions will get separated. CO2 plus and H plus goes to cathode, Cl minus and OH minus goes to anode. Now, who do we choose to discharge at cathode? We do a quick recap. At cathode, our selection for discharge is always based on this factor called the ECS. And according to the ECS, you are supposed to pick the one that has the lower position. All right, so therefore, between CO2 plus and H plus, if you have memorized your ECS, you will agree with me that CO2 plus is the one that has lower position. So CO2 plus will be picked to discharge at cathode. Now, how about anode then? Anode, remember there are three factors that affects my choice, right? I have to first figure out what's my factor. You always ask yourself according to this flow, is it type of electrode? Is it concentration or is it position in the ECS? Okay, so the first question to ask myself, is this electrolysis going to be affected by type of electrodes? Now then to answer this, you go back and look at your electrodes. Over here, you are using the normal carbon electrodes. So therefore, type of electrode, this factor is not applicable. Okay, that's one. Now the second question to ask myself, is this going to be affected by concentration? Now I look at the solution and I look at the figure. It's 0.001. And on top, they give a title as dilute. So this solution is not concentrated. So therefore, concentration is not applicable over here. If it's not type of electrode, if it's not about concentration, that means to say my anode is affected by, again, ECS. And once I've picked this factor, I will follow the rule. The rule of ECS says I'm supposed to pick the one with lower position. And this 2 goes to anode, right? Cl minus, OH minus. Who has the lowest position? Answer is OH minus. So this one will be picked to discharge at anode. Now, once you have made the correct choice, now the next thing is you just need to work on the half equation to show people what's happening. All right, so cathode, they will get discharged, right? So at cathode, I need to write a half equation to show discharge process. So I start off with the ions that I discharge, which is copper. Based on my recap just now, positive ion discharged by accepting electrons. So CO2 plus will accept 2 electrons and turn into Cu. Now, on the other hand, what happened at anode? At anode, because you have chosen OH minus, so your half equation should tell people what happened to your OH minus. So my OH minus will discharge, right? And it becomes oxygen and water. All right. So negative ion discharged by throwing electrons, right? Not so over here. Now, so OH minus donates the electron. It throws to the back. When you have electrons at the back, it donates electron. Then you have a product oxygen and H2O. So now you need to balance the equation. I will put a 2 here. So next I will, because I need to balance my O and my H, right? So I will first put a 2 here. And now totally I got H2, 2H2, sorry. I'll put a 2 here instead. Okay, so now I balance my OH in front. So total I have 2 oxygen here and another 2 oxygen from water. Total I have 4 oxygen. So in order to balance it, I will put a 4 in front. Now then the next thing, do not forget, before you do any balancing, right, when you only involve 1 OH minus, you will only donate 1 electrons. But now that due to your balancing, you include, you need to balance and make it 4 OH minus, therefore you will donate 4 electrons. All right, so that's a half equation for it. Okay, now next we do overall ionic equation. As usual, overall ionic equation is the combination for both half equation. So I need to rewrite my half equation. Okay, so over here, how do I combine both of them to become my final answer? So to do this, again, the key is you have to balance your, you have to cancel off your electrons. Now, in my first example, the numbers of electrons is the same, so you can just cancel straight away. However, in this situation, your number of electrons is different, so you couldn't cancel them straight away. You need to do a modification. So what I need to do is, this whole entire first equation, I will times 2. I will times 2, and the purpose is just to make the electrons the same number as below. All right, so now I times 2 already. So what will I get is, I will get 2 Cu2 plus, here becomes 4 electrons, and here becomes 2 copper. So I times 2 already, so this is my product. Now, once I'm done with this, now I can safely just cancel off my electron. Whoever in front of arrow put together, whoever behind the arrow, and you put together. So therefore, I have 2 Cu2 plus and 4 OH minus in front of the arrow. So I put them together. Arrow, then put those at the back, 2 Cu plus O2 plus 2H2O. All right, so this is my half equation. All right, let me just do this nicely for y'all. Okay, so that's my half equation. Okay, can you understand? So now we look into the observation. We look into our observation. Okay, so again, just like I've mentioned, in electrolysis, right, you will have a minimum 2 observations, one at cathode, one at anode, and sometimes your solution will also give you some observation. Okay, so how do I answer my observation? So I will ask myself, what happened at cathode and what happened at anode? At cathode, I've discharged the Cu2 plus and I've turned it into a pure copper. And pure copper is a solid and it's brown color. Therefore, at cathode, I'm able to see that brown precipitate is formed. Right? Brown precipitate is formed. Now, how about at anode? At anode, what happened is I discharge my OH minus and oxygen gas is being released. Water you couldn't see because it will be mixed in your beaker, but you have managed to see oxygen which appear as gas and it is colorless. So at anode, I'll be able to see colorless gas is produced. All right? So again, if we ask you why at cathode you see brown precipitate, your reason is because Cu2 plus Cu is formed. And anode, why do I see colorless gas? Because oxygen gas is formed. All right. So remember the one in bracket is explanation. They are not observation. Observation is as highlighted over here. Okay. All right. So from here you can roughly see. All right. I'm actually for the first 2 diagrams, I'm using the same chemical, exactly the same chemical. It's just that for the first one is molten, there's no water, and the second one I dissolve my copper to chloride in water, and the result is very different. All right, so this is how we differs the electrolysis of molten compound and its solution. Okay, so now we look at another scenario. I'm still electrolyzing the copper 2 chloride solution. I'm still electrolyzing this. All right, but the difference is that just now I was using a dilute solution, and now I need to work with concentrated solution. Now let's see how this affects my answers later. Okay, so you have to set up, all right, and you can see this solution is 1 molarity, more than 1 means it's concentrated. Okay, the minute you turn on electricity, again, the cations and the anions will get separated. Because I'm still working on the same solution, I will expect to have the same cation and anion, right? So I have Cu2 plus and Cl minus, H plus and OH minus. So the cation will be moving to cathodes and anion will be moving to anodes. Now, as usual, once ions have reached respective electrons, we need to choose them for discharge. Not all of them will get discharged. Only one will get discharged at cathode and one to discharge at anode. So the next question is, who should I choose at cathode? Now, based on what you have, I've mentioned, at cathode, you don't have to crack your head to think who to choose. You choose based on ECS, all right? For cathode, for all situations, you just go by ECS, and ECS asks you to choose the one with lower position. So again, between this pair, Cu2 plus and H plus, who has a lower position? Cu2 plus. So Cu2 plus will be chosen at cathode. Next, how about at anode? Now, recap, at anode, it can be affected by 3 factors, right? It can be affected by type of electrode, concentration, and ECS. So we have to ask ourselves one by one. The first factor, type of electrode. Is this electrolysis affected by type of electrodes? To answer that, I'll be looking back at my electrode. It's made up of carbon. It's not even a metal. So therefore, type of electrode, this factor is not relevant. Now, how about the second one, concentration? I will focus on my solution, ask myself, is it concentrated? And the answer is yes, because the word concentrated means already concentrated. Or you can see from the figure, it's above 0.5, it's already concentrated. So which means to say in this particular case, my choice at anode is based on concentration. And according to this factor, I'm supposed to choose the chemical ion instead of water ion. So we go back. At anode, I have 2 ions, Cl minus and OH. Which is the one from water? OH. Which is the one from chemical? Cl minus. According to the rule, I'm supposed to choose the chemical ion. Therefore, in this case, the chemical ion Cl minus will be chosen for discharge. Okay, you see the difference. Just now, when you do with normal dilute solution, you choose OH minus due to the factor of ECS. But now when you increase the concentration of the solution, your choice at anode is different. All right, now you choose based on concentration and therefore you choose chloride to discharge instead. Right, let me highlight to you the difference. The difference is at the anode side. Okay, so you have made your choice based on the factor available. And now again, we build the half equation to show people what's happening. So at cathode, you have chosen Cu2 plus to discharge, and Cu2 plus discharged by accepting electrons. So the same thing, Cu2 plus accepts 2 electrons, and it turns down to Cu. So it gets discharged. Now at anode, all right, so in this case at anode, you have chosen Cl minus, right? So we start with Cl minus. Remember, negative ion discharged by donating electron. So it will donate 1 electron. So 1 electron will be donating out. And next, when it discharges, means it goes back to normal. Chlorine acts as a diatomic molecule, so Cl2. Now, in order to balance the equation, I will first need to balance my chloride just to make the Cl number correct. And because 1 Cl minus donates 1 electron, Since now I use 2Cl minus, I'll be donating 2 electrons instead. So I need to balance it accordingly. So be very careful when you need to balance equation, balance for half equation, right? Okay, so now you have your half equations ready. Now, how about the overall ionic equation? So you will do the same thing. Overall means you need to combine both half equations together. So see, this is how I do. I copy back my equation, half equation cathode and anode. All right, so again, for you to recap, the rule to combine them is to cancel off the electrons from both sides. So in this case, the number of electrons is the same, you can just cancel it. And once you're done with that, whichever in front of arrow you will put together, that is Cu2 plus and 2Cl minus. Then whichever behind the arrow you will put together, Cu and Cl2. All right, so that is my overall ionic equation. Okay, next, how about the observation? What will I observe for this particular electrolytic setup? All right, so I believe that all of you will agree with me that at cathode, because what happened is I discharge my Cu2 plus and it forms Cu, which is a brown solid. So what I observe at cathode is that a brown precipitate is being formed due to formation of copper. Now at anode, what do I see? You see at anode, you discharge a chloride and you form a chlorine gas. Chlorine gas is yellowish in color. So therefore at anode, I managed to see greenish yellow gas is formed. Greenish yellow gas is formed. It's produced. All right. So for those who need to explain why is it that you see greenish yellow gas at the end of the day, because based on my half equation at anode, chlorine gas is formed. All right. So you can see whenever you make a different choice, your half equation will be different, your overall equation will be different, your observation will be different. So that's why whenever you need to choose these ions to discharge at anode and cathode, you have to be very, very careful. So you just follow the rules that I've mentioned, and if you do it slowly, you can avoid making careless mistake. All right, so we have one more to go, the last one. Now you electrolysis of dilute copper 2 chloride solution. You are still working on copper 2 chloride solution, but now the difference is that I'm using a copper electrodes. So you can see the setup. Same CuCl2 solution is dilute because you can see 0.001, and we are using copper electrodes. So again, to analyze it, whenever I turn on electricity, the first thing is the cation and the anion will get separated. Because it's the same solution, I have the same cation goes to cathode, same anion goes to anode. And now I have to make a choice. Who should I choose at cathode and who should I choose at anode? So again, at cathode, all right, the factors that affect your choice is always ECS at this moment, right? So therefore, between CO2 plus and H plus, you will be choosing CO2 plus. However, at anode, it can be affected by 3 factors. Now let's see, is it about the first factor? To recall, first factor is type of electron. So you ask yourself, is this electrolysis affected by type of electrode? To answer this, you focus on your electrode. Hey, I'm not using carbon, I'm using copper, which is a pure metal. So therefore, in this case, my anode, the choice will be affected by type of electrode. And to do a recap, the rule of type of electrode is anode itself will donate electrons. You don't choose anyone, but anode itself donates electron. So therefore, we choose none. Okay, so you can see, right? Now when you use different electrodes, your choice again is different, it's being affected. Now to write half equation at cathode is the same at cathode because you're still choosing your CO2 plus, so your half equation will be the same. Now how about at anode? You say you don't choose anyone, then how do you build a half equation? Even though you are not choosing any ions to discharge, but your anode itself donates electron. And you ask back yourself, your anode is made up of what? Your anode is made up of copper, Cu. So therefore, my half equation starts with Cu, which is equivalent to the anode. So anode donates electron, so Cu will donate electron. Guys, we all understand when Cu donates electron, it always donates 2 electrons. And it will turn itself into ion Cu2+. Okay, so this is what happened at anode. So remember, the Cu is the anode itself, right? So anode itself donates electrons to the back and it forms Cu2+. Now, in this case, the next thing is we need to do overall ionic equation, right? Let me adjust this for you. Now, we need to do overall ionic equation, but in this case, overall means you have to merge these two together, right? You will realize that if you really merge it, everything will be cancelled off. So for this case, there's no overall ionic equation to discuss. Okay, right. Now, how about observation? All right, what is the observation that I'm able to see at cathode and anode? Now at cathode, you are forming copper, right? And please be reminded, you are forming copper at cathode, right? And please be reminded, yeah, your rod is also made of copper. So the metals will just stick together. So you will expect there will be, when you form copper, the copper will stick around your original copper electrons. And due to that, your observation at cathode is that cathode becomes thicker. All right, now if you want to know the reason why, this is because Cu form, all right, will precipitate around the copper electron. All right, now how about at anode? At anode, based on your half equation, what happened is that your copper, your anode, throw electron. It undergoes oxidation. Due to the fact that it's releasing electron and turning into ion, at anode, what you can see is that anode becomes thinner. Reason is because anode donates electrons and form ion. Okay, so now you can see it is very different, right? Okay, so now from here you can roughly have an idea. Even though I'm electrolyzing the same chemical, but when you have a different condition, let's say molten or dilute or concentrated solution, your choice to discharge at cathode and anode is different, and that leads to a different half equation and different observations. All right. So the universal rule is that at cathode, at your level for SPM syllabus, you always remember your choice will always be based on ECS. And if it's ECS means you will pick the one at the lower position. But for anode, it can be affected by either type of electrons or concentration or position in ECS. You must first pick the factor correctly, then you choose your ion according to the factor. Okay, now before I end with this discussion, there's one more that I want to discuss with you about observation. Now, based on what I've mentioned previously, I mentioned that when you run an electrolytic cell, you will have a minimum 2 observations. There will be one at cathode, one at anode. Sometimes your solution might show color change as well, all right, depending on the type of ion that it contains and how the concentration changes. So so basically for electrolytic or molten compound, you will not see any observation on the color change. But color change are quite obvious when you involve copper solution. Right, we do a quick recap. Any solution that has copper 2 ions inside, it's usually blue in color. Right? Why is it blue? It's because of the presence of Cu2+. And if a solution has more Cu2+, the blue intensity will be very high. But if the concentration of the Cu2+ is less, the blue color will be quite pale. So now let's see what happened to the blue color of this solution. So we look at the first example where we have the dilute copper 2 chloride. At first, my solution is blue because it's Cu2 plus. Then, what happened during the electrolysis process? If you go by the half equation, during the electrolysis process, you are using up your Cu2 plus and you turn it into a Cu. So therefore, in this case, what you can see is that you have used up your Cu2 plus. So the concentration of Cu2 plus ion decreases right now. So due to the fact that there's less and less Cu2 plus, one of the observations that you can see in your setup is that the blue intensity of CuCl2 solution decreases. This is what I see. All right, the blue intensity of CuCl2 solution decreases, right, for this particular setup. And why is it so? To explain why, because concentration of Cu2 plus decreases. Okay, next, moving on. How about my cell number 2 where I use concentrated Cu2 plus? So again, my solution itself is blue at the beginning because of Cu2 plus. And according to my half equation, again, I'm using up my Cu2 plus. So what you expect is blue intensity of CuCl2 solution decrease again. All right. Now, how about the last one? Yes, my solution is blue at the beginning due to Cu2 plus. At my half equation at cathode, I realized that I'm using up my Cu2 plus, I'm discharging. But at anode, hey, I produced the Cu2 plus back. So one hand you're using it and one hand you're producing it. So at the end of the day, there will be no changes in the blue intensity. So this is an extra note. So no change in the blue intensity of CuCl2 solution. Right? So there's no changes. Huh? All right. So if people ask you why is it there's no changes? Because concentration of Cu2 plus remains the same. And if we ask you why it remains the same, because the rate of discharge of Cu2 plus at cathode is the same as the rate of formation of Cu2 plus at anode. So one hand you discharge it, one hand you produce it back. So there's no changes in the concentration. Okay, so with that, we are done with this consider quite long recap of electrolysis setup. Hope you guys understand from there.